because we were talking the last weekend a little bit of about this model, and also that we are gonna discuss about this paper this week. So I invited her and she accepted. So it's pretty nice to hear directly from here about this paper, right? So I don't know if you want to introduce yourself, maybe.
Sure. Thanks for the introduction. Thanks for the invitation. So I'm Miryam. I just started as a professor at KU Leuven, where Vladimir is doing his PhD. And so this work is mostly with people from University of Copenhagen, where I was a postdoc, and Liz Zaleski, who inspired the work originally. Just a quick disclaimer, credits go to my authors for the slides. They've all given this presentation one by one to very different institutions, and for me this is the first time I'm presenting it, and so they had good slides, so I'm just taking them. So this paper is about language modeling with pixels. The motivation is, you've probably seen this kind of figure a million times, showing how much the current language models have scaled and become like more and more, using more and more parameters. And the scale has really changed the face of NLP, really, for at least languages like English. We're doing much better than before on many benchmarks. Well, the blessings of scale have some kind of a curse. When you are working in academia, you don't usually have the resources needed for building the big language models. But that doesn't mean that there's nothing you can do. You can still work on smaller models and maybe try to make them not bigger but smarter. And this is what we try to do with Pixel, and like more specifically, we want to make them smarter in a way that they can deal with more written languages, because the benefits of scale have not really shown enormous success in multilingual NLP. The field of multilingual NLP is booming, and there's been some progress, but there's this thing of the curse of multilinguality that is clear and that is very much unsolved. In particular, there's a problem of the constraint of the number of uncodable tokens, so the vocabulary. If you add more tokens to your vocabulary, you get computational issues in your softmax. If you have fewer tokens, then you get a problem of sequence length, and I'll make this clear later. So if you have a vocabulary of characters, you just get a longer sequence. Which, if we were only working with Latin alphabet, you would still get somewhere, but when you get to two languages not written in Latin, then you have bigger problems. So what we call this the vocabulary bottleneck, and this is kind of summarized here with different types of models. So Word2Vec has a vocabulary of size of 3 million, which is quite big. If you work with FastText, you have 200,000 vocabulary, so this is a lot smaller and more manageable. BERT has 30,000, that's not so much. But that's just for English. XLMR has 250,000. It's okay. It's still doable, but there is still a huge limit as to how well XLMR works for. There's a limit. It's not working for all languages. Far from it. So then a solution is to use bytes. And so these are the multilingual models. But then you get long sequence lengths, and also a bias in the scripts that UTF is originally made for languages for Latin script, and then extended to other languages, which are then to other scripts, which are then encoded in longer sequences. And then this canine used UTF-32 and has a still pretty large vocabulary and long sequence lengths. So the worst of both worlds, arguably. So what we claim is that we can crack this vocabulary bottleneck by rendering text as pixels. And this allows to essentially not have a vocabulary at all. Instead of having a softmax and decide on the next word, you essentially learn to reconstruct patches of pixels. And the motivation for this work is, as I said in the beginning, so Liz Selesky had a paper where she developed a machine translation system that encoded the source side as images, essentially, and then that had a pretty normal decoder. And this model, mask autoencoders, are scalable visual learners. They showed how to efficiently train a transformer for image reconstruction. So how does Pixel work? The input is text, but can include images or emoji. And it's the first thing that we do is to render it as an image of patches of 16 by 16 pixels using the Google Noto fonts and these Python libraries to render the text, Pygame and PangoCaro. These are projected and position embedding is added. And then we mask spans of patches. So that's a slight difference with the model with, that we use, where they just randomly mask different patches in the image. Here, to make it more adapted to text, we randomly mask different spans with some probabilities as for the length of the spans. These are so then fed to an encoder, which has 12 layers, pretty standard, and is trained with a mean squared error loss over the reconstructed, so the patches that are masked in the input. So they're compared with the reference from the sentence and then trained. The text renderer is flexible. It can render emoji. It uses RGB. It can render left to right and right to left languages. So here we have an example of, I believe both of them might be, no, I guess Mandarin, is it? No, Mandarin is left to right, but Arabic is right to left. And then the last example here shows word level rendering, where essentially you add blank space to make sure that the patches correspond to exactly one word. So you don't want to have an overlapping patch with two different words. The render text is compact. So here is the distribution of sentence length for universal dependencies tree banks in different languages, and it's a comparison of pixels. So this pink dotted line, the reference is the tokenization in universal dependencies, and then we have BERT and MBERT, and we see that for Arabic and Japanese, clearly pixel is a more compact representation than the rest, and in general, it's pretty compact. How does it work for fine-tuning? So we had an encoder and a decoder. We don't need the decoder at fine-tuning time. We just take the encoder and just essentially do exactly the same as for encoding a sentence for pre-training, except obviously we don't mask anything. And then we fed the representation output to here for it's a sentiment analysis. No, it's a true or false. So I guess it's a fact verification or whatever task. And so the softmax layer learns that task. So the benefits of pixels are that pixel can process anything that can be rendered. It's open vocabulary, so it's easily extensible to unseen text, and it supports all written languages. It has complete parameter sharing from the input representation, and that's that's unlike separated or related subwords in an embedding matrix. So it allows similar words to be represented similarly. Now we pre-train on the English Wikipedia and books corpus. This was for direct comparison with BERT. Originally this was the kind of a base experiment, and it gave very interesting results. So we made this the paper. We use 25% span masking with patches of length 529. Used 8 GPUs for 8 days, so I think that's also comparable to BERT, and the parameters are also comparable to BERT, so 86 million for the encoder and 26 million for the decoder, which again we throw away at downstream at the time of downstream tasks. A quick note: there's a study that looked at the data used by BERT, and some of it, but a very small minority, is actually non-English. So it's not like it hasn't not seen at all other scripts or languages. And so we have now a new type of generative model. And here we can see the patches reconstructions over training with, we can see that it gets better over time. At least these ones get better clearly over time. It still struggles with it's still not perfect. It struggles with, I'm not sure what the slides is exactly showing, but it still struggles. It's not perfect. So then the downstream tasks, downstream experiments, we used universal dependencies tree banks, Masakane, NER, and Zero-A. And we compare with BERT-based, that's the main comparison. We also compare with Canine, which essentially is trying to solve the same problem, but obviously they train on a lot of languages, so it's not directly comparable in terms of the data it's pre-trained on. So this is really the main comparison. And in terms of dependency parsing results, Pixel vastly outperforms BERT on unseen scripts, and this is not really the case for Latin scripts. At least for English, we don't. BERT still outperforms Pixel. And partially this can be explained by the fact that for BERT, obviously, a lot of these unseen scripts are unknown. So here, the line under the graph here shows the percentage of UNC tokens that BERT sees. So obviously for Coptic, most of it is UNCs, so it's obviously not doing anything sensible, because it just cannot learn anything based on UNCs. But this really shows that that Pixel overcomes this vocabulary bottleneck, where really you can do better with pixels, and it directly can be used for unseen scripts. So for named entity recognition in African languages, we see a similar pattern where, depending on the script, Pixel does better than BERT. And surprisingly, Pixel actually almost always outperforms Canine, which again has seen a lot of data from a lot of different languages. So this is really shows the potential of Pixel. And then we wanted to see how well it does against adversarial attacks, because the idea is that we think that images are going to be more robust to small changes in the input, because obviously, because it's not characters, it sees the similarity in slightly different characters. So we compare BERT and Pixel on a variety of adversarial attacks, and overall, obviously, both models, the accuracy of both models decreases with the attacks, but clearly Pixel suffers less than BERT from these attacks. So clearly it's learning something. And finally, we also wanted to look at code switching. Is Pixel better for code switching language, where so the input is in different languages? And here the conclusion is still the same. For Latin scripts, it's not really the case. But as soon as you have code switching in so Hindi and English, so in a different script, then you actually get performance improvements from using Pixel over BERT. In future work, we want to scale to multilingual pre-training. Obviously, it will be interesting to see what it's like when we train on many languages. We also would like to look at cross-credit transfer and what happens and how it works. Is the convolution embedding layer learning something, or the whole stack? And then one interesting direction is also to use pixels as a single interface for multimodal learning. So use a combination of images and text and have a shared representation and see what we can learn. So to conclude, Pixel is a new type of language model where no textual input is unseen if it can be rendered as an image. We achieve high quality transfer to task on unseen script, and the representations are robust to attacks that are orthographic, and we can also deal with code switch text. Yeah, that's it. Thank you. Obviously, happy to take questions as much as I can answer. My involvement with the paper was mostly with the evaluation. So there are some details about the rendering and training that I might not know, but feel free to ask away and we'll see. Yeah, Felipe.
Thank you for your presentation, Miryam. It was really interesting, and I think the idea is really great. I was wondering if you guys test like to using this technique to enhance the information that is given to the input. I was thinking like maybe you can color the different words with different colors, like giving the model more information about that you can you can manually give the model more information for it to process that you would be able to do using only the text.
That's an interesting suggestion that I don't think we've thought of. No, I don't think we've thought of that. So you mean using color or images or emojis?
I was thinking like
and manually adding.
Yeah, like if you have the parse tree example, you could, I don't know, give some colors to to different levels of the tree, and like build the tree that way, and maybe enhance the information that you're giving explicitly to the model for a given task.
That's interesting. I don't think this has come up yet. I will suggest it. This is interesting.
I was Carlos has maybe some synergies.
We have thought of because our parsing experiments are based on pre-tokenized, so gold tokenized text, which obviously is an assumption that you can't make in practice, and that's definitely future work needs to look at how to predict this tokenization, because obviously the downside of not having a vocabulary is that it's not clear how you tokenize text and then compare to your reference. I still think that we can learn a tokenizer. I apologize for the police sounds. My street is very police busy. I hope it doesn't bother you too much.
I can barely hear. Don't worry.
Okay, good. What was I saying? That so we can. I'm sure you can learn a tokenizer Yeah, that would be one thing. It's not really answering a question. I was just also going to say that we have thought of doing parsing as a kind of linearized. So I don't know if you've seen these papers where they learn parsing. So they linearize trees and learn essentially a language model over linearized parse trees. So essentially, instead of really learning to build a tree, you just pretend that your text is you linearize your trees, and you pretend that your linearized trees are just normal text. So this is where I think that the colors could actually be in this kind of framework. Then colors could probably easily be added, and then we could learn such a model. Yeah, interesting suggestion.
I think it's interesting. You have so much flexibility with the images that you don't have with the strings. It's really interesting work. Thank you, Miryam.
Thanks.
I see that Valentin has a question, and then I'll ask one after.
Yeah. Hello, Miryam. Thanks a lot for the presentation. It was really, really interesting. I was wondering, what about handwritten data? You were mentioning tasks like sentiment analysis, and this could be awesome because you have like a lot of latent information about like the mental state of the writer that are encoded in the way you are like writing. Also, a lot of doctors now use tablets at the hospitals. Doctors are known to have like a really difficult written skills, difficult to understand, and for like I don't know, the manuscript of some books. So for emotion analysis in text, something like that. Thanks a lot.
Thank you. Yeah, I don't know if there was a question, but yeah, OCR is definitely an application that we haven't looked at yet ourselves, but that's definitely one of the things that we're thinking of, and that I'm sure other people are thinking of. Using directly bypassing OCR. So if you have a document with annotations, then you can completely bypass the OCR, and that would be really cool. And I'm sure someone will do it, if not us, because it's an obvious application. Or you just train the model to do OCR. Hopefully, it can also do something there, and then you can directly use. Then you can directly use the model on handwritten text, hopefully.
Thank you, Miryam. So first of all, thank you for the presentation. Very inspiring work, by the way. My question, I have two questions, by the way. First one is, if you could dig a little bit in how you use this model for downstream tasks, because for BERT, you have some sentence level tasks, such as classification or whatever. And also you have, like, as you said, the parse tree, which is word level. But when you render this phrase, you don't have that kind of separation, or not as clean as we would like. So how you deal with that?
Yeah, so that's related to the tokenization issue I was mentioning. So we cheat a little bit, like I said earlier, that we use gold tokens. Depending on the task, we do different things. For post tagging, we just or at least for NER, we just use the first patch representing the words. Essentially just imitating what previous work has done. Like with BERT, it's also pretty common to just take the first subword. And for dependency parsing, we do the equivalent that was done with subword pooling, but then with patches. So you take all the patches of a word and do some pooling. and then learn a combined representation of all of these patches. Again, this uses gold token information, so it's like I said, a little bit of cheating, but the model that we compare to do this cheating too, so it's kind of fair. But yeah, of course, in the wild you need to do something about this, and I think that yeah, like I said, you can just train Pixel to do tokenization, and then obviously your accuracy will decrease, but so will the accuracy of the competition. So it's just like that. I don't know if that answers your question.
Yes, perfect. Thank you. I thought the answer would be like that, but I was curious.
Yeah.
And the second question is regarding how do you think these models are representing information? Because in BERT you have a one-hot output that if you think for some phrases, the mask token could be one or maybe two or maybe three right answers, and the model has what BERT does is that it outputs a probability for any given token.
Yeah.
But when you are trying to reconstruct the image, it's not clear for me that the model is trying to balance maybe these two possible answers, because they will be messed up. How do you think about how the model deals with it?
Yeah, I mean, it's obviously this is an open question, and I guess exactly what Pixel learns and how is a question that we're certainly going to explore a lot more. Now, we do have some visualizations of attention in the paper. They're not included in the slides, but so there you can see what words the model attends to. Still, like you can visualize where in the sentence the model attends. So it is still possible to do some visualization of attention. I don't know if that answers your question.
Yes, it does, in fact.
Okay.
I was wondering, with your answer, I'm thinking that maybe this model is exploiting another kind of information that BERT cannot, which is the length of the words. Because in BERT, you just know that there's a single word there, but you don't know if it's a long or a short phrase. But when you render it, you know that you have to fit a word that fits that length. So
yeah, that's right, and at the same time, I mean so you know the length, that's true, of what you're reconstructing. Now it does not necessarily have to be a word, right? So the span masking is random, and the span does not have to correspond to a word. So I think we could see this in this figure. Yeah, you see some of these spans go over several words, and maybe this is what the slides was showing, that if you have a too long a span and spanning too many words, then the model starts struggling.
Thank you, Miryam.
Thank you. I think Marcelo had raised your hand. Yeah.
Yes. Thank you for your presentation. I have some doubts that are related to the question of Carlos, are very similar. In terms of what are you really encoding in the language model? Because when we work with text, it's very easy to understand that we are coding charts or words or subwords.
Yeah.
In the case of rendering text, it is not so easy to see what are you encoding in the language model, in the basic language model. Are you encoding these scripts? Can be compositions of short words, can be short words, can be subwords. This is very, very unclear for me. Do you have an idea what is what is the basic level of coding that is working in this language model?
I mean, I'm not sure. So one thing I want to say is that it's true that it's more difficult to interpret these models, because indeed you cannot just compare you cannot easily compare the representation of two similar words and do like you often do with that's more used with like static word embeddings, where you really can see topic models and stuff. So it's probably fair to say that you lose a bit of interpretability with Pixel compared to BERT. Do we know what it learns? I mean, it does seem to learn something about the tasks. So you can get some confidence that it is learning something about language at this point already. Clearly, there's also a difference in how well it learns about syntax as opposed to semantics, which we have been thinking, and we want to work on this, could be due to the fact that there's no really long-term objective. So there's no, like in BERT you have next sentence, mass language modeling and next sentence prediction, and we don't have the equivalent of next sentence prediction in Pixel, which makes it more difficult to learn long range dependencies and sort of document level features. So that's certainly something we're thinking about, and hopefully this could make the model learn something better. Yeah, I don't know if that really answers your question. This is really early work, so knowing what it learns is still very much an open question. It does seem to learn something about language.
Okay, and I have a second question that is related to the question of Valentin. Did you check the language model with manuscript text?
So you mean, have we tried with handwritten or
yeah,
we have not yet. That's definitely in the things of in the list of things to try. There's many things.
So it supposes that you have a pre-processing step where all the text is using the same font, for instance.
Yeah.
Okay.
It is so we have there was quite a bit of work in like selecting exactly the font that can actually render all these scripts. But yes, everything is rendered using the same font. We have experimented a little bit with different fonts, and it is somewhat robust, at least at the time of downstream applications.
Okay. Thank you. Thank you very much.
Thank you.
Okay. It seems that there are not more questions.
No, I have a little.
Okay, you go first. So.
Yeah, thanks, Miryam, for your presentation. It was very motivating. So I think that the most line to follow is a multimodal.
Yeah.
Like if you represent with images the text, it will be easier to carry that words to the same space as images. Yeah. So have you tried something like that? Like
not yet. That's definitely also in the pipeline. I also think I think like
clip performance.
Yeah.
Where they have to create an embedding of the text and the image from two sides and like compare them in the same latent space. Yeah. Maybe with your method will be, I guess it will have a better performance.
Yeah, that's my guess too. I really think that this will have an impact in a multimodal setting. Yeah, it's one of the many things to try, but it's clearly an obvious one and with high potential.
Yeah, it was not a question, like
Yeah.
suggestion.
Yeah. Thanks. I take suggestions, of course.
Okay. My question is like, what do you think is the best idea to improve this model in the other kind of languages? Just to increment the corpus of those languages, or?
Yeah, that's a question we're exactly thinking of right now. I think, I mean, there's two questions. There's the question of improving the performance, and there's the question of scientifically where can we get. And from a scientific point of view, I think it makes sense to go smaller first, just have fewer languages, but hopefully cover a large variety of scripts, so that you can see if there's some kind of cross script transfer happening. And if you train, most interestingly, I think things like, if you train on Chinese, how well is it going to do on Japanese? So because right now we've only tried with Latin, that can transfer clearly to other alphabets, but I think really like looking at logographic languages might be more interesting.
Yeah, because it's quite impressive that, for instance, in the paper you have like the percentage of, well, also in your slides, the unknown tokens for the different languages, and also the pre-trained corpus was the BERT model. The same as BERT model, right?
Yeah.
Exactly. It's like how small was the percentage of other languages? Like less than
it's
1%.
It's less than 1%. Yes, it's right here.
Yeah, and even that is like, for instance,
which
in
is
Korean, is like very high in comparison with BERT.
Yeah.
So if it's only 1% of the corpus, so it's like, it's very impressive, because it means that actually the model is learning with few examples, maybe, let's say, in terms of that big corpus, right?
Yeah, so you mean BERT is not doing so bad?
No, I mean your model is like learning with very
like this.
examples.
Yeah, exactly. Yeah, I mean, essentially, I think it's certainly just a better starting point for a downstream task. I mean, we do fine tune it on all of these languages, right? So it's not clear to what extent it actually uses the original representation. So maybe it learns everything from scratch based on pixel representations, but it's clear that it's a better starting point, at least.
Yeah, it will be nice to evaluate the representations.
That's something that exactly. That's something that I've been interested in seeing, if it really, if at fine tuning time you're using still something or learning something completely different. That I think that would be interesting to see.
Miryam, and what about the computational complexity, or how much time did you train the model?
Yeah, similar to BERT. I think this was here. So 800 GPUs for 8 days. So it's
okay.
Similar to BERT. Yeah. We have a few more details about.
This is from scratch, like the first time you created the images from text, you trained the model from scratch and took that time.
Yeah. We have a few more details about computational complexity in the paper, in the appendix, but essentially it's comparable to BERT. The rendering part can be made more efficient still, but it's still not so far off from BERT tokenization.
Nice.
And do you know if the time of retraining was equivalent to the BERT model also?
So I don't remember the numbers exactly for BERT, but I think it's very similar indeed.
Yeah, okay.
And Valentin has a question.
Yeah.
What is the size of the data compared to text-based model?
I'm not sure. What do you mean by text-based modeling?
Compared to birds, I think.
Compared to the size of
The text
We used
versus
exactly
images,
the
I guess.
same.
the same.
Okay, right. Do you mean okay? I don't remember that. I think that's must be in the paper. I think it's comparable, but I cannot guarantee you the same number.
I remember that in the paper you said that you need more space for images in the hard disk drive
Right.
to compare with the text.
Yeah, that's
But
right.
yeah, and the thing is that you will try to solve it like doing the rendering on the fly.
Right.
So try to optimize the rendering is the solution.
You know the paper better than me, Vladimir.
Miryam, have you tried this approach with a generative model like GPT-3 or whatever? Because this is
Yeah, I was
more in the
wondering.
more in the birds flavor.
Mhm.
Someone is working on this. So yeah, someone is trying this. I don't know where she got at this point. But yeah, that's work in progress. We're thinking.
Yeah, I also was wondering that because I remember that previous to mask language modeling or this mask approach, everything was like generative in a sequential way, even for images. So, and it worked really well.
Yeah, I mean that's clearly one open question in this paper. It's obviously not directly generative or autoregressive, and that's an interesting direction to try.
Good. Someone else has a question? Yeah, seems no one has another question, right?
All right, then.
So
Thanks
yeah,
again
thank
for
you,
inviting
Miryam,
me
for
and
attending.
for all your great questions.
Thank you.
Thank you to you. It was really nice to have you here and to discuss a little bit about your paper. Hopefully to see you again in another meeting with the guys of Chile.
Gladly.
Yes.
Have a nice day, everyone. Have a nice evening, Vladimir.
Thank you very much.
Bye.
Hi, thank you.
Bye bye. Have a good.